Therefore, we proposed an improved distance transform. In this distance transform, a comprehensive geographic information model is built. All needed data for alignment design, including the digital elevation model, forbidden zones, the cost model, the unit cost model, and soil conditions, ground subjects such as the vegetation of the ground, and the railway design parameters are stored in this geographic information model. Then we defined a generalized distance, that is, to link two cells in our study area. The link cost is defined as the distance between these two cells. That is the comprehensive cost in our model, in our optimization model, is the generalized distance. Also, to handle the complex constraints, we also developed several methods for handling constraints. First, an adaptive neighboring mask is designed. The basic neighboring mask in the distance transform algorithms is a multiple n metric. However, in complicated mountainous regions, such basic neighboring masks may not be able to find feasible paths. Thus, we can expand this basic mask until a feasible local path can be found. This is our adaptive neighboring mask. Lastly, we proposed a bidirectional scanning strategy. That is, we first set the start point as the only target in the study area. Then we set the end point as the only target. The two targets will effect separately to generate two distance maps, and these two maps will be combined to generate the final distance map, and thus many promising paths can be generated rather than only one promising path in the basic distance transform. After the global path generated, after generating the global passes, we select the best one, that is the least cost one, to refine this path, and then set cutting plans at each key point to generate the railway corridor. In this corridor, the genetic algorithm will effect to search for detailed alignment solutions. Here comes our improved genetic algorithm. Some basic conceptions are that the cutting plans are sized to generate horizontal point of intersections and vertical point of intersections, both for the initialization and optimization processes of the GA. The locations of HPIs and VPIs are denoted as genes. Sequences of these genes are combined into an alignment chorosome. Then, selection, mutation, crossover operations are developed to optimize the alignment through generational evolution. The advantage of this algorithm is that it is efficient in optimizing alignments in areas without great topographic complexity. That is, in the flat plane regions, the genetic algorithms are generally applicable or feasible. However, determining the appropriate distribution of the cutting plans are difficult in mountainous